Hello. Hello. Yeah, that's fine. What is that? Just wait for 2 minutes. Yeah, 2 minutes will wait. Otherwise, uh, 10 o'clock lectures mean 5 minutes this. I'll just take few minutes time to talk about Lyapunov stability. Yesterday, while teaching Lyapunov stability, I gave you the concept of Lyapunov stability, and intentionally, I gave some wrong answers just to think over that, because you are academics, okay? And I will pass on the other lecture handouts, which will be circulated to you. Professor Rahul Kaur will circulate that, right? What is the things? While you teach the people of the students in your class, don't talk to them what I'm going to talk now, because they will unnecessarily get confused, right? What I teach last time, you just teach them. You see, I have got a nonlinear system. I have got a nonlinear system. Written that. Yeah. Now I have got a nonlinear system x dot is equal to f of x, right? I'll tell you, this particular system has got multiple equilibrium points. Multiple equilibrium points, right? So what we do in the linearization, we compute the Jacobian, each of the equilibrium point, we find out the eigenvalues, and we say whether the system is stable or system is unstable, right? Lyapunov stability, yesterday what I gave you the answer, the Lyapunov stability is we study entirely for all equilibrium points, which is not true. Lyapunov stability also is studied with respect to each of the equilibrium point. Got a point? For each of the equilibrium point, not all. But don't confuse the students, you see. Don't confuse the students. Each of the equilibrium points. The catch I will tell you what the difference. Otherwise, if that is the case, then what the difference between linearization and that one? There is some difference. I'm coming to that point. So what happens? See here, this definition, very careful see it. Consider the zero input nonlinear system x dot is equal to fx. So you will say that if it is zero input, is it applicable for any other input? Yes, it is possible. Because input is a function of the state variables, so this becomes essentially zero input. Assume that the system has got a unique equilibrium point at the origin. This is the assumption, right? But the system doesn't have a unique equilibrium point. System has multiple equilibrium points, right? So the question is, first thing I'll tell you, step number one, again repeating the point, while teaching the students, don't tell all these things because they will confuse. Step number one, transform the equilibrium point, any equilibrium point you are talking about, you are analyzing equilibrium point into the origin. First to do these things. Suppose you have got a system, it has got an equilibrium point, say at +1, you transform that one into origin and change the equations. Just step one I am explaining here. Step one, I will come back again. See here. Given a dynamic system, x dot is equal to fx, and equilibrium point x satisfies fx is equal to 0. To analyze Lyapunov stability at xc, we typically do a coordinate shift. So this has to be done for each of the equilibrium point. We first decide which equilibrium point you want to study stability. That equilibrium point may not be at origin. That equilibrium point may not have origin. If not in the origin, you transform it into origin by a suitable transformation by Z. Now this actual system is x dot is equal to fx. Now the system which you are studying is not x dot is equal to fx. It is z dot is equal to f z plus xe. Right? Now this particular system, the equilibrium point is always at origin because you have shifted it. Got my point? So the equilibrium point now shifted to origin by suitable transformation. Then you examine, then other things are straightforward. Okay? First thing, so each of the equilibrium point which you are interested, you transform it into origin and then do it. So in the standard Lyapunov theory, it is implicit. We assume that the origin the equilibrium point. We always assume the origin the equilibrium point, and with respect to that origin, everything we are doing it, right? Now the next question is, very simple question, we can do it. Then what is the difference between that and the linearization method? What is the difference? Because you are trying to analyze the system stability around the equilibrium point by the linearization method. And here also you are analyzing the system if the system operates within the Origin, okay, origin is the equilibrium point now, right? But it's not the case. When you take a Lyapunov function, that Lyapunov function has got an area. If you plot it, so here what happens, I will just tell you these things, very subtle things actually. The origin is the equilibrium point, right? Linearization method, linearization method will tell you if the system operates within a small region, whether it's stable or not. Lyapunov stability is different. It is origin, no doubt about that. But what happens? First you assume a Lyapunov function, then you differentiate. If it is negative, system is stable, right? That Lyapunov function will decide by what range. This is the Vx function. That means if the system, suppose the system is stable, that means system is stable if you operate not around the equilibrium point, but in this particular region. Okay. So what happens, the students when they do the research, what they will say, I have got a system, I took this Lyapunov function, then I found the system is stable. Then another student will say, the same system, I took this Lyapunov function, this system is stable. That means the second person's approach is more better than this one. Another person will say, I took another Lyapunov function, this system is stable. It is not around the equilibrium point. It is around the area defined by the Lyapunov function. So for each of the equilibrium point, you have to find out what is the, whether it's stable or unstable. So here you see, I will pass on to you, all examples are here. This point is important. Lyapunov stability is always with respect to a specific equilibrium point. It is not, as I told you yesterday, not for all equilibrium points, specific equilibrium point. So the equilibrium point where you want to study the stability, first transform that equilibrium point to the origin. Then start analyzing it. Next point is how it is different from the linearization, because in linearization you are taking you are assuming the system operates within a small region, but here you don't assume that. Here you take a Lyapunov function, so the people say this is the stability information based on this Lyapunov function. By changing the Lyapunov function, the stability information may change. Got a point? So that is the point. Lyapunov stability is always with respect to a specific equilibrium point. So we cannot say a system is Lyapunov stable in general unless we specify which equilibrium point is being considered. Right? This is for you to know, but for the students, don't tell these things. You just take, assume that the system has got only one equilibrium point at the origin and analyze the stability. Got a point? So, therefore, I intentionally, when you asked, is it general? I told you it is general. No, it's not. Each equilibrium point, because that's a point, still more things are there I cannot discuss here. There is a basin of attraction you have to see. Each equilibrium point has got a basin of attraction. So, the Vx region which you are taking, if it is covering the entire basin of attraction of that equilibrium point, that is always good. So, two examples I have given here. So, this note will be passed to you. Don't read the other notes, right? Okay, now let us go. Unfortunately, no. No methods. Until 200, more than 150 years now. No other methods. No other methods have been developed. Feedback linearization. There is one thing that is called the Jacobian linearization. The linearization which you are talking in general, they are essentially Jacobian linearization. X dot is equal to fx. You find the Jacobian matrix del f over del x at x is equal to x star. X star is the equilibrium point. Okay? And then you start designing this thing, Jacobian linearization. You linearize the system around the equilibrium point. Okay. There is a nonlinear system. You assume, find the equilibrium points, Jacobian, all these things. There is another niche one is the feedback linearization. It is completely different than the Jacobian linearization. Feedback linearization, what it will do, if the system has got some nonlinear element, the controller will completely remove that nonlinearity out. Right? I'm giving the example first. Many nonlinear systems cannot be controlled effectively using linear control techniques, PID, LQR, due to intrinsic nonlinearity. The basic idea is to algebraically transform the system into linear one and apply the linear control techniques. Is it same as the conventional linearization? No. Feedback linearization is achieved by exact state transformation and feedback and complete cancellation. Now see the example here. Now here, x1 dot is equal to x2 and x2 dot is equal to minus ax1 minus cx1 cube plus u, right? Now, there is a component minus cx1 cube, nonlinear component, completely cancel it. You see, if I select u is equal to cx1 cube plus v is the new input, right? Then to cancel the nonlinear term minus cx1 cube, then this cancellation results in a linear system, you see. This cancellation will result x1 dot is equal to x2 and x2 dot is equal to minus ax2 minus bx2 plus v, and v now you design. V is your new control input, right? So in this case what you do, you completely cancel it. As I told you yesterday, the analogy, earlier system is nonlinear, you ask them that you operate in this particular region, don't disturb other people, right? We just request the person, I know that you are an idiot, but please don't disturb other people. You just operate within a small region, right? But here, no. You are an idiot, get out. Okay, completely cancellation, right? Now, then you design the controller. Any controller can be designed, doesn't matter. Again, is C. While fitting any models to a system, as I told you, you must decide why you are fitting the model. As I have told you, you must decide why you are fitting the models. Otherwise, modeling is not a fun, right? If you want to design an adaptive self-tuning controller, you represent the system by a discrete parametric model, right? Because you see the derivation starts from the discrete parametric models. If you want to design a state feedback controller, the system must be x state is equal to ax plus bu, not parametric model, right? Similarly, if you want to design a state feedback linearizing controller, the system must be represented by this structure. X dot is equal to fx plus gx u and y is equal to hx. Right? Now see here, this particular transformation is called the affine class of nonlinear system. Affine transformation or affine class of nonlinear system. X dot is equal to fx plus gx u. That u is important, no u dot. No u dot or no u square. If your system, nonlinear system has got u square, okay, then you make some arrangement, some transformation to bring it to u. The system must be represented in x dot is equal to fx plus gx u. Fx is nonlinear, gx may be nonlinear, but it will be u is important, you see here. This is u, no u square, no u dot, and y is equal to hx. And usually hx is a scalar. And pose the question whether there exists a state feedback controller alpha x plus beta x v which will make this system linear. I have got a nonlinear system, x dot is equal to fx plus gx u, y is equal to hx. And I have got a controller u is equal to alpha x plus beta x v. Is it possible to transform the system into a linear system, right? Now, I'll come to this point. Change of variables will come later on, just a minute. Is it possible to cancel the nonlinearities in every nonlinear system? Feedback linearizing controller, is it possible to do it for all systems? Or such cancellation is possible only in some class of nonlinear systems which satisfy certain structural property? I'm just reading these things here. To cancel a nonlinear term alpha x by subtraction, the control u and the nonlinearity alpha x must always appear together as u plus alpha x. See, I want to cancel something, right? I want to cancel something. If that nonlinearity is added, then I can subtract it. If it is multiplied, then I can divide it, right? That is what he is saying, right? To cancel a nonlinear term gamma x, which is multiplied, so you have to cancel it by division, then something different has to be done. This point will save. Thus, feedback can convert a nonlinear state equation into a controllable linear state equation by cancelling nonlinearities if the nonlinear system is represented by a nonlinear state equation of the form x dot is equal to ax plus b gamma x into u minus alpha x. Okay? So, see here, this is clear. If the state equation, you see x dot is equal to ax plus b gamma x into u minus alpha x is a nonlinear system, right? If the system is in this form, this point is extremely important, I am telling you. If it is in this form, now see, by if I make u is equal to alpha x plus beta x v, if I make u is equal to alpha x plus beta x v, where beta x is equal to gamma inverse x. Now what will happen? Can you just tell me? You see, I am doing it here. X dot is equal to ax plus b gamma x, right? b gamma x into u minus alpha x. Now u minus alpha x is equal to beta x v. U minus alpha x is equal to beta x v. Now beta x, now beta x into gamma x is equal to identity because characterized by gamma inverse. So naturally, if the system is in this form and you are using a controller like this, it will convert it into this one. Right? Now then you design any controller. If the system is represented in this form, then by using a controller of the structure U is equal to alpha x plus beta x v, beta x is equal to gamma inverse v, you can convert it. Now suppose it is not in that form. Suppose it is not in that form. It will be that form, it is quite straightforward. If it is not that form, it is quite straightforward, you can put it. If it is not in that form, let us see. Suppose the system is not in that form, not represented in this form. Can you apply a control law which can make it linear? Right? Now see, one thing I must emphasize here, the concept state variable model of a system is not unique. I will give an analogy to make it clear. State variable model of a system is not unique. You can have infinite number of possible things by suitable transformation. Say for example, x dot is equal to ax plus bu. You can define a function, another variable x is equal to pz or z is equal to p inverse x. You can define another variable. So this system will be z dot will be p inverse apz plus p inverse bu. The same system can be represented by this, where p is a constant full rank matrix. How many possibilities is there? Infinite number of possibilities. State variable model is not unique. So we explore these things in your controller design. In the controller design, what we do, sometimes we diagonalize the system and then design the controller. Similarly, if a nonlinear system is not in this form, you transform the nonlinear system into this form. For linear system, you can transform it by suitable choice of P matrix. You can select P matrix, so it becomes controllable canonical form, observable canonical form, diagonal canonical form. All these people who knows control theory, they know it. Similar thing, you can do it for nonlinear system, right? And then start doing it, okay? I will tell you the example how this transformation works. How this transformation works. When my son was studying in school, during that time this, what is that, PS2, PS3, Xbox, this is no longer there nowadays. Is it there? PS2 is there? PS5 works something because my son is married now, so I'm become old, don't refer that. So he's not playing with that. PS2. So during that time there's some Xbox was there. He will always say, if I tell him every day I want what I do, I will say no matter what happens, you must study every day at least for 1 hour. And I have got a sheet of mathematics. You have to do mathematics, nothing doing. Nothing doing. And he will always switching, as children, you know, always switching on the television, seeing the cartoon also, always. I went to Professor Virakumar's house. His lovely daughters, younger daughters, always switch on cartoons. It's a universal phenomenon. It's not with. So the father, as a father, you will always get irritated. It's a usual thing, you see. That's a very standard thing in all houses. Xbox, he will never listen to me. He will not do the mathematics. Okay. He'll say, okay, I have done 10, I will not do 20, all these things. So what I do, I keep that particular sheet of mathematics in my car back seat. So he will go to a St. Luke's mall. There's a mall there. big, beautiful mall. In the mall, in the first floor, I park my car. The moment you come, there's a EB Games. The name of the shops, EB Games. Before I enter somewhere, he will straightway enter into EB Games and find out which games are there. Xbox. $135, I remember, during that time, $135, $70, $80, not less than $70. He will say, okay, this game, this is good, this is good, this is good. He said, I will buy it. I'll tell you, wait. I'll listen to you. You come to the car, there is a mathematics sheet, you just go and do it. Then we'll talk. Now he will go there and he will immediately scribble and do the mathematics, then he'll come back. You got a point? Now see here, this child who was not obeying, who was completely in an uncontrollable mode at home, the moment he went to the shopping mall, now it is controllable. Transformation, you see, how easy. You see, I cannot control him at home, but I can control it in the shopping mall. I'll tell that, okay, I will buy you this thing, PS2 games, provided you do these things. You got a point? So similarly, this transformation sometimes works, many times. If it is not controllable here, not controllable in the controllable definition sense, that is not. If it is not possible or it is difficult here, transform. Clear? Do you understand these things? It works in many cases. Many cases, you transform it, okay, and do it in the other domain. Say, for example, this is our home. This is our home, difficult to control. You transform to the mall, shopping mall, see here. And do the job there. Clear? Any time you do the transformation, remember, any time you do the transformation in practice, not in forensic is different, biometrics is different. Any time you transform to other domain, other place, that transformation must have an inverse. You should be able to come back. You should be able to come back this way. If you cannot come back, you are in trouble. This transformation which you are doing, you are applying, it must have an inverse. That means you are going in this direction, you must come back, right? If you cannot come back, it is a big problem. Because you are going to shopping mall, you will vanish. Right? I always give this example there also. In India and epics, we have gotten this inverse transformation did not exist in place of Abhimanyu. He entered into the Chakravyuha, we could not return. See, they killed him. It's a serious thing. Inverse transformation does not exist. Clear example there. He entered into the Chakravyuha, do not know how to come. He doesn't know, right? So this is the question of inverse transformation. One-way traffic. One-way traffic. One-way traffic means you are going in one way, you cannot come back. Okay. In linear systems, while it transforming, you consider a matrix P which is invertible. That means inverse transformation exists. For nonlinear system, exactly the same thing. The transformation operator, which is invertible, is not told in nonlinear system as a full rank matrix. It has got a name, it is called a diffeomorphism. Geometric quantity is diffeomorphism. Diffeomorphism. You use a diffeomorphism T. So Z is equal to Tx. Transform X to Z, where T is a diffeomorphism. What is diffeomorphism? It is inverse exist. Because T may not be a standard matrix which you are talking about. Okay? The same thing, concept is same. So anytime you do the transformation, it must have inverse, right? not in biometrics. Because there the transformation which you were using should not have an inverse. Should not have an inverse, otherwise people will catch it, people will know it. Non-linear transformation, that is a different issue. Okay. When a change of variable, z is equal to tx is used to transform it because I want to put it in that form. T must be invertible, it must be an inverse map, x is equal to T inverse z. Since the derivative of z and x should be continuous, it is necessary that both T and T inverse must be continuously differentiable. And a continuously differentiable map is a diffeomorphism. This is all in the geometric. Feedback linearization is coming under the area of geometric control theory. Okay. See here, I am writing a continuously differentiable map with a continuously differentiable inverse is known as diffeomorphism. So, forget about all these complications. I have got a system that is in this form now. If it is not in this form, I have already made it into this form, then I will design a controller and cancel it. Right? I will cancel it. Only small mathematics. Without that, we can talk actually, very small mathematics. Y is equal to hx. Y is equal to hx. So delta h is equal to del h over del x1, del h over del x2 onto del h over del xn. Okay? That is the definition standard thing. Standard y is equal to hx. This is a scalar, y is a scalar. So del h is equal to del h over del x1. X dot is equal to fx plus gxu. Now I am defining one thing, del f, fx means f1, x1 and f2, depending on the number of state variables, right? This is del f1, this is a matrix, del f1, del x2, del f1, del xn, and simply del fn, right? Now, I need only one mathematics here. I am defining on Lie algebra that is called Lie algebra. This one will take some time to digest, but doesn't matter. LFH, just see this thing. LFH is equal to del H over del X into F. LFH. LFH is del H over X. F is a vector. F is a vector. So del H over X into F. This is called the directional derivative of H. This is called directional derivative of H in the direction of F. Directional derivatives. So LFH is del H over del X into F, right? And similarly, there is a simple thing, LF2H is equal to del LFH by del X into F. Okay, so this way. I am not entering into that thing because unnecessarily you will get bored. So this mathematics I require a little bit. The Lie algebra, simple Lie algebra, directional derivatives. Yeah, no, this mathematics I require, not necessarily you are interested. What you are interested, while deriving that thing, we require this being easier to do this thing, nothing else. Without that also we can do it, but it's always better. Given a scalar function hx, the directional derivative here is defined. Because I need this mathematics. I may not need it, but sometimes it is always better to do this LFH. Lie derivatives, Lie algebra. Lie is the name of the person. Okay, I think they are Norwegian mathematicians or something like that. Which one? No. Lie algebra is not necessarily required for that. Lie algebra is necessary because when you are deriving, it is easier to represent these things. Not necessarily we can represent. Some people, mechanical engineering, have taught it. They say, no, don't teach Lie algebra for feedback linearization. You just teach in normal. That is possible. Okay. But this becomes easier actually. This is only simple mathematics. Not necessarily. See, LF0H is H and this term. Similarly, LGLLFH is equal to LGLFH is equal to, so see from the right hand side, del of LFEH by del X in the direction of G. So whatever is there here, G, it will be multiplied here, last. Suppose I will say like this, LG LF2H will be del LF2H over del X into G. Always see the right hand side, entire right hand side you take it and multiply. Suppose I do very LX1, LX2, LX3, LX4, that is called to derivative of LX2, LX3, LX4 divided by del X into direction of X1. That is the point. Everything from the right hand side, you differentiate and put it there, right? This is the only Lie algebra. One thing, relative degree. Then we will discuss a little bit relative degree. Relative degree is, suppose you have got x dot is equal to fx, y is equal to hx, we will define that. Now first let us do a little mathematics. X dot is equal to fx, y is equal to hx. What is y dot? Y dot is equal to h dot into x. I am doing it here, then it will be clear. Y dot is equal to del h over del x into x dot. Because y dot with respect to time, so y is hx. So first I differentiate with the x and x dot. And what is x dot? That is equal to del h over del x into fx. Right? And that is by definition is LFH. Similarly, y double dot, d over dt y dot, so this will be LF2H, right? Differentiation. If x dot is equal to fx, another one mathematics, then I will close it. Other things we will discuss. Now suppose x dot is equal to fx plus gx u and y is equal to hx. Again let us do it. What is y dot? I will come back to this point. What is y dot? Now see here y dot. This much only understand. What is y dot? X dot is equal to fx plus gx u. Y is equal to hx. Now y dot is equal to del h over del x into x dot. That is equal to del h over del x. This much of derivation I will do it actually, otherwise you cannot understand. Plus gx u, right? That is equal to del h over del x into fx plus del h over del x into gx into u, right? Del h over del x in the direction of f is equal to LFH. Del h over del x in the direction of g is LGH into u, right? That is equal to y dot. Now if LGH is not equal to 0, if LGH is not equal to 0, Then you see, by selecting the input 1 by LGH minus LFH plus V will give you y dot is equal to V. Clear? Right? If LGS is not equal to 0, then you can select this input and it will give you a linear relationship between the output and input, right? And similarly, if it is 0, further differentiate. We'll see to that now. And correspondingly, you will find we'll give an example. I'm not entering mathematics now. How to find out a linear relationship between the output and a pseudo input. That is the objective now. So the idea is, forget about Lie algebra. You have got an output. We'll do it in an example, it will be clear. You differentiate the output until U appears. And then you cancel it. Let us do it, right? And a number of times you differentiate until the U appear is called the relative degree of the system. Let us do an example, then you see. Definition, these things will come later. Now see. Consider the Van der Pol oscillator. X1 dot is equal to X2, X2 dot is this one. Determine the relative degree of the system when Y is equal to X1. First let us see. Relative degree is important. I will tell you why it is important. What is relative degree? Differentiate Y until U appears. The number of time you differentiate until U appear is the relative order. Right? Now Y is equal to X1. Let us do it. Differentiate Y. So what is Y dot? Is equal to X1 dot, right? Y is equal to X1, so Y dot, I am differentiating once X dot. What is X1 dot? See the equation. That is equal to X2. Is U is appearing? U is not appearing, right? Again differentiate. So Y double dot, that is equal to X2 dot, that is equal to minus X1 plus epsilon 1 minus X1 square into X2 plus U. U is appearing or not? So what is the relative order then? 2, right? Now let us say change Y is equal to X2. Y is equal to X2. If I change Y is equal to X2, if I make Y dot, what is Y dot? X2 dot. Is the U is appearing? So if I check Y is equal to X1, the relative order is 2. Y is equal to X2, relative order is 1. Number of time you differentiate until U appears. No. Output is just at Y is equal to Hx. Yeah, relative degree is dependent on how you are defining. If your output is Y, the relative degree is Y is equal to X1, the output is 2. If output is X2, the relative degree is 1. In this system, right? So relative degree depends which one is your output. And the output is a function of state, X, Hx. No, not necessarily. Not necessarily. Not necessarily. X1, this one, and then we will go. X1 dot is equal to X1, X2 dot is equal to X2 plus U, Y is equal to X1. What is the relative order? Relative degree. Same thing, differentiate Y until U appears. Now what is Y? y is equal to x1. You differentiate it, y dot is equal to x1 dot. What is that? x1. You see these things? This is the equation. Y is equal to x1. I differentiate y. So this y dot is equal to x1 dot, that's equal to x1. U is appearing or not? No. You can differentiate. What you will get? Again x1. So no matter how many times you differentiate, you will not get it anything. Right? So therefore, this system doesn't have a well-defined relative degree. It doesn't have a relative degree. So feedback linearization is not possible here. We can do it. Okay. System should have a well-defined relative degree. No, why you do 10 times? Right, that is a good question. If the system order is n, 5 order, okay, so you can be at least x1, x2, x3, x4, x5 or xn maximum. So 5, fifth order means y can be 5. So maximum you can go to 5, fifth differentiation. There is no point in doing in the sixth differentiation. So relative order will be always less than equal to the n. Relative order is less than equal to. Okay. I will do the example, things will be clear. This is called, there are two types of feedback linearization. This is a very powerful controller, that's what I'm telling you. Even nowadays you go to a journal, you will find many people are publishing papers on this feedback linearization controller. Input, output linearization, that means there is a relationship, linear relationship between input and output. Another is input state linearization, which is a complete linearization. Because, okay, input output linearization or input state linearization. Input output linearization is relatively simple. Relatively simple, not really simple. And what happens here? If the system order is equal to n and the relative order is equal to 2, then it gives you y double dot is equal to v. What is the dynamics of the system? 5. This example, suppose I am taking n is equal to 5, right? The relative order is 2. That means you are getting by a control law y double dot is equal to v. That is a linear relationship between y and the new control input, right? Another 3 things left because the fifth order dynamics, system dynamics, right? So while doing input output linearization, which is relatively easy, you must find out. First of all, let me give the example, then the analogy, then you can, otherwise you cannot understand. You see, I am here. You are 20 people here, right? So I have got good relationship with 15 people. Relative degree is 15, not 20. If relative degree is 20, then I have got a linear relationship with all the 20 people, right? So y 15 is equal to v. That means I have got good relationship, linear relationship. How many people? With 15. Another 5 people, where are they? So those people can go and talk to a director that this fellow is talking nicely to all the 15 people and he is not talking to us. You got my point? So I must ensure that's fine. I have got a good relationship with the 15 people, but rest of the 5 people with whom I do not have a good relationship, they should be sober and gentle. Those are called the zero dynamics of the system. Dynamics of the system which are left out. Zero dynamics. You see, the typical term in feedback linearization, zero dynamics. We will see now one example, zero dynamics. Because YR is equal to V, so now it is under your control. But the rest of the things, where are they? The zero dynamics, that means the dynamics which does not have a linear relationship with the output, how they behave. You understand this point? I have got a good relationship with 15, other 5. What is the dynamics? Their dynamics is 0. Why it is zero dynamics? Remember here, that is another interesting thing. Suppose the last bench, 5 people, I don't have a good relationship, right? How they behave, I have to check it, their behavior, when you people are not here. Because when you people are here, with whom I have got good relationship, they will not speak out. So I will tell you 15 people, I have got good relation, that's fine, I will manage, you better go out. You go out. The rest 5 people, those people I do not have good relationship, I could not linearize it, then I will ask them, please don't mind it, okay? Those people are, that's fine, you are also special, don't be unstable. Then I will check their status, otherwise those people will be irritated, what my point? So zero dynamics has to be studied. Input, output, the linearizing controller must study the zero dynamics. That because those dynamics which you eliminate, you don't do it, you study the dynamics. You understand, otherwise there will be a problem. You ignore some people, it's a horrible stuff, you know, because if you ignore it, so zero dynamics should be must be stable. The dynamics of the system, when all the state variables which are being linearized become 0, everything. You study their dynamics. So there is a method in which you study the zero dynamics, right? Now, if the relative order is same as the system order, then there is no zero dynamics because I am linear with all the state variables. Okay? So there is no zero dynamics is not present because I have got good relations with all the people, right? So that is a method in which you have to do it. There is a method, I am not explaining the methods because we don't have time to do explaining these methods. Have you studied feedback linearizing controllers anywhere? This is not being taught in the undergraduate. It is taught in the postgraduate. Master's level course they will teach, or some students who do PhD, they study feedback linearizing controllers. Very powerful controllers, extremely powerful controllers, okay? So, I have given in handout because I don't have time to explain you how to calculate the zero dynamics. All the steps are here and the zero dynamics must be stable, okay? And you can design, there's a program here, I don't know whether it's there in the assignment, how to design a feedback linearizing controllers. All the things are here, the program is also there, computer program, you better do it. Any other questions here? I'm just giving the concept here, because there is no time, we have to go to the, any questions here? You take a system, if the system is not in a particular form, you apply a transformation. The transformation must be a diffeomorphism. Then you transform it. Then what you do, you differentiate the output until U appears. Then design it. Then there is a straightforward. This is a straightforward thing. Just cancel it. If the relative order is not equal to the system order, which is always the case, most of the cases is the case, you must study the zero dynamics. Understand the concept zero dynamics is a very important concept. Because those people will be violent. The unstable zero dynamics is not tolerated. Zero dynamics unstable, that will be, rebel in the system. Because YR is equal to V and the rest of the things, where they will go. Zero dynamics, if there is unstable zero dynamics, there is a possibility to stabilize it. If the zero dynamics is unstable, that is called a non-minimum phase nonlinear system. It is not, yes, nonlinear system is called non-minimum phase if the zero dynamics is unstable. A linear system is a non-minimum phase if there are zeros in the right half of this plane. So we have a controller to design for non-minimum phase. Similarly, you can design, it is not unstable. The zero dynamics is unstable. Okay? So that non-minimum phase non-linear systems. I have got a rotary inverted pendulum, zero dynamics, unstable zero dynamics, non-minimum phase. We have got a student working on that, so non-zero dynamics. Sometimes zero dynamics is unstable, but remember who are the zero dynamics. See the concept. Concept should be clear. They left out. I was watching a couple of days before coming to New Zealand. I didn't have time because I was too busy. I was watching the Ramayana serial. And when Indrajit put the Lord Ramachandra and Lakshmana in a Nagapass, then she have to tell zero dynamics. I'm talking zero dynamics. Don't think I'm talking Ramayana. So he went to Vaikuntha to call Garuda to come. And in that episode, not in the Raman Saga Ramayana, so this episode, the Garuda is telling, Lord Hanuman is going and asking Garuda, you please come and help the Lord. The Garuda is zero dynamics, unstable. He told, no, I will not go. Why the Lord did not take me with him? He took his Sankha, Chakra, Gada, Padma. He took, all these things. Sesanaga as Lakshmana, Sankha as Bharat, different parts became his brothers. Why the Lord did not take me? He left me in the Vaikuntha and he took all other people with him to Mortelok, right? So I will not go. That is a clear example of zero dynamics, unstable. He's telling, no, I will not go. I will not go and help. Then Hanuman told, no, there is a purpose for that, you come. You got my point? The clear example of zero dynamics unstable. Because he left out, ignored. He's thinking we are ignored. So he's feeling bad. Standard thing. You got my point? If you are ignored, why you will do it? So input-output linearization, you must be careful about the zero dynamics. Right? Other things are straightforward. Right? Any other questions? Difficult to know, because this one I took at least 5-6 lectures to teach. Lie algebra, 1 lecture. How can you teach all these things? Zero dynamics, concept of zero dynamics. At least I have got some story to tell, therefore I could do it. Otherwise it becomes difficult. Concept. Any questions? Feedback linearization is not a robust controller. That is the problem. Feedback linearization, usually, if the model is not accurate, this will be error. Because you are cancelling these things, right? So if the model is not accurate, it will give bad results. But do one thing, you apply 2 things. First, linearize, crude control, and there is some sort of uncertainty. You do it, supplement it, some other controllers. Got a point? So that is how the strategy has to be used. Yeah, there are ways to do with zero dynamics. Yeah, multiple loop you can put it here. But feedback linearizing controller becomes so powerful controller, there's no doubt. But if the model is imperfect, it becomes difficult. Implement is not issue. Implement is issue. The little bit issue because there is a division operation. U is equal to U, sum divided by that. So it might be, but still I will consider this one of the powerful controller. Because it completely cancel out. That's the point. Completely cancel. No. Okay. Completely cancel out. Get out. If you have nonsense, get out from this place. Input to state linearization is little more complex. There are certain conditions has to be satisfied. That conditions are involutive conditions. That involutive conditions is also a bit more more involved actually. Oh, the span of the matrix should be this. All these nonsense things. Oh dear, is difficult. I have taught twice the state feedback, state linearization. The student says, Dr. Swami, just leave us alone. Yeah, feedback lineage control. Even now you go to journals, you will find many people are using feedback lineage controllers. Yeah. Because very powerful controller. Because first thing it will cancel out non-linearity. Some other imperfections are there that will take care. That will take care. So, we'll take a break now or 5 minutes break? Now you can go and move around 5 minutes. 5 minutes is not 5 minutes. 5 minutes is 6 minutes, 7 minutes. is on the, on, yeah, hello, yeah. Yeah, you take it. So we are almost at the end of the course, huh? Is there anybody here who is working on genetic algorithms? Yeah, genetic algorithms. That's good. That's good. Okay, so we should start now. Now let us see the optimization problem. Let us see the optimization problem. I have got a function and I want to find out what is the maximum value or the minimum value of the function. Now the general thing is, if I have got a function f of x, then to find out any extremum, we can say maximum, minimum, doesn't matter. So what we do, we differentiate with respect to that and make it 0. Correspondingly, we find out, forget about that second derivative, all these things, that I am not talking about. You take a function and differentiate that particular function and find out what is the maximum value. Let us say maximum value or minimum value, right? So those type of optimization techniques which we have studied in schools, in colleges, they are called the derivative-based optimization. They are called derivative-based optimization. Derivative-based optimization. Okay. You take a differentiation, okay, a differentiation. But as I told you, derivative operator is a very serious operator which should be avoided under any circumstances. Because when you are differentiating, many cases, many functions, the differentiation doesn't exist, right? So a new class of optimization techniques were developed and which is called derivative-free optimization techniques. Most of the bio-inspired computing in general, say genetic algorithm, particle swarm optimization, say ant colony optimization, random forest algorithms, all these things, and essentially, evolutionary competitions, essentially, if you see it, it optimizes a particular function and gives you a solution which does not require any derivative. It is a derivative coming under the framework of a derivative-free optimization. There is no derivative operator there, right? Is no derivative operator. Got a point, the concept here? We usually do the derivative, differentiate and find out, but which is not the case. GA belongs to a class of derivative-free optimization techniques, DFO methods, right? DFO methods do not require any gradient or Jacobian, no differentiation operation, suitable for discontinuous functions or noisy objective functions, complex simulation, black box model. You see, discontinuous functions. Discontinuous functions. What is discontinuous functions? When the functions are defined, jump discontinuity, right? Jump discontinuity here. Now at this point, what is the value? It is value is +1 or value is -1. How do you know? Got a point? This point, right? Jump discontinuity, right? So GA-based methods are derivative-free optimization techniques. Do not require any gradient, right? And you can optimize certain things. Genetic algorithms, so most of the bio-inspired computing, they say it bio-inspired computing, right? Usually, bio-inspired computing, right? So this is essentially optimization algorithms. Now these things are being used in many applications, in control, in signal processing, in identification. Many places these things is being used. Okay, concept is essentially optimization. Let's see, derivative-free optimization. And is iterative. Okay, we'll see to that. So, I'll tell you when I first attended one the talk in genetic algorithms when I was in Sheffield. This Peter Fleming, who has written that genetic algorithm toolbox for MATLAB, he has got many students. One student was presenting something. He was using some terminology, you see, genetic algorithm terminology, population, genes, chromosomes. I did not get anything out of that. What the hell is talking about? This is a control department. What is talking? Chromosomes, genes, population, crossover operator, mutation operator. What is that? You should, just like in the next lecture, I will talk about the reinforcement learning controller, agent, state, environment. What the hell is agent, state, environment? I always ask when 2018, I've got a student doing PhD from Guangzhou in China. So she was doing PhD on the reinforcement learning controller in power system. We have published papers in transactions, industrial informatics. The same thing, Joey came to me, she's a girl. Joey told me agent, environment, state. I told Joey, don't talk all these languages. You make a presentation where you map it. What is the meaning of agent in control parallels? All these things, right? So similarly, initially I did not have a clue. Just like I told you, where I didn't, what problem I have faced, I'm sharing with you because I have found a solution now. Diphontine identity, I was surprised. Consider diphontine identity. Where does the identity is coming? Why it is coming? That we do not know, right? So what happens? Genetic algorithm is a derivative-free optimization algorithms. So what it does, it has got some way to do it. So what I do, suppose I have got a function f of x, say x is q plus 10x to the power 5 minus 7x to the power 9, like this. Now I want to find out, I plus 10 x absolute value of x. Let us say, I want to find out what the value of x, what the function has got a extremum. Minimum or maximum doesn't matter. So what I will do, I cannot use del f over del x. I cannot use, because that is x bar x. Okay? So that function differentiation doesn't exist. So what I will do, I will search. I am not solving, you see. I am not solving any gradient optimization. I will search. Okay. So I have got, let us assume, x has got some, let us take arbitrarily. Randomly I will generate some values. Randomly I will generate some values. X is equal to 1.2, 1.5, 2.4, 2.5. Just randomly, what I will do, because I cannot do these things randomly, generate some values of x. randomly generate, right? Say for example, I'm telling x is equal to 1.2, minus 2.1, 3.5, 7.9, minus 10.2, like this, okay? Now, what I'll do, I'll generate some random values. Each value, I will compute what is f of x. I will compute x at each value which I have generated, right? Then find out which value gives me the maximum or the minimum. Got my point? Suppose I cannot differentiate, so what I am doing, I will generate randomly. I will generate randomly, then some values, and substitute those values in the function and find out what is the value there, and then see which value gives me. Let us assume the minimum value problem, let us say, for this lecture, where the fx is minimum, right? You do anything, doesn't matter. You do anything, you generate few samples. You generate 5,000 samples. You generate 5,000 samples, any matter you generate, I am not bothered. Okay. Now suppose, because you have all your own limitations, suppose you generate some value between minus 100 to plus 100. Suppose you generate any 20,000 pairs of values between minus 100 and plus 100 and put it into x and compute x value, then find out which value of x the function is minimum, right? Now let us assume I found fx is minimum when x is equal to 91.234. Right? I found out because I calculated all 20,000, 50,000 values. Is it the true answer? That is the question. Suppose the true minimum value of x, the value of x where the function is minimum, suppose it is minimum when x is equal to minus 402.5. Suppose the function has got the minimum value, the true solution is minus 402.5. Now you have generated a random value between what and what? You will certainly get one value where the function is minimum. But that is not the actual minimum. The global minimum is lying there in minus 402. Right? Anyhow, so this is a sort space. This is a sort, you define a sort space. You understand where I am coming from? I have got a function. I want to find the minimum value. I can do the usual way, differentiate that function, but I cannot do it because the differentiation doesn't exist, that thing. So what I do, I generated random values between some limit and limit, and for each value, I will compute this particular function, right? Then I will certainly get a solution, no doubt about that. But is that solution true? This is not true in this case. The function has got true minimum value at minus 402, but my sort space is minus 100 to plus 100, right? Okay, understand this? So we are not entering into that. So what you do here, let's come to this point first. If you are not using derivative-based optimization, you generate a set of possible solutions, minus 100 to plus 100, let us say, you generate random numbers, these are called the set of possible solutions. It may not be the solutions, set of possible solutions, right? And for each possible solution, you compute the objective function, fx, that is the function, okay? this set of possible solutions in genetic algorithm has got a name. You generate a set of population or chromosomes, each chromosome. Okay, the chromosome is one of the possible solutions. Minus 2.2, minus 3.4, okay? Chromosomes. Chromosomes are a set of possible solutions. A chromosome is one of the possible solutions, and the set of chromosomes is a population. Okay? All is minus 100 to plus 100. So when the genetic algorithm first term is a chromosome, the chromosome is nothing, you see, it is a possible solution. It is a possible solution. Just like here, some number. But normally what we do, this possible solution, I am not talking about real-time genetic algorithms, possible solution is usually binary coded. It is possible to real code, in particle form we do it, but doesn't matter. Now let's say binary coded. So that number instead of minus 2.1, it is a binary string. See here. Suppose I have got a string, a binary string. One possible solution is 1 0 1 0 1 1 0 1 1 0. So this is one of the possible solutions. Okay. So another binary string, another number. So these are the binary strings depending on number of bits. You define a range. Okay. So you generate the possible solutions. Suppose you generate the chromosome, 4-bit chromosome, binary string. So that means your possible solutions is between, forget about negative numbers, say 0 to 15. Possibility 0 to 15 or depending on negative number, doesn't matter, right? So chromosomes are the possible solutions, okay? And the solutions are actually real, no doubt about that. They are numbers, right? But we encode it as a binary string, because that we will see why you are using it binary strings. That will come later on. So GS has got chromosomes. There is a term called chromosomes. Generate a set of populations with many chromosomes. Okay. Then what we do, let's see. Is it coming? It's not moving? Yeah, moving here. First, you define a set of possible solutions. That is a chromosome. Okay? You will do it today in the assignment. Say, for example, my function is a 3-variable function. x1, x2, x3. My function is 3-variable functions. So, I don't know which value of function, it is minimum, right? So I will define a possible 3-variable chromosome. 3 chromosomes you see here. One set is, suppose 12, 6, 9. So 12, instead of 12, 6, 9, I can generate 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, right? I generate. Okay. Yeah? Here, this is one chromosome. This is one chromosome, okay? And this represents 3 number of variables. That you know, the 3 variables. Each variable has got 4 bits. Each variable is represented by 4 bits. And there are 3 variables, x1, x2, x3. And this is a chromosome, right? Similarly, I generate a set of chromosomes. That means it's a population. Not only 12, 6, 9. I generate, say, 10, minus 5, 3. This way. So this is a chromosome. Encoding schemes provide a way of translating problem-specific knowledge directly into GA framework and thus play a key role in determining GS performance. You have to encode it. Okay. In the program, the MATLAB program, very simple. You just give a random number, it will generate a random string, right? Then here, as I told you, see here, I'm explaining what the meaning of that. Let us take only one set of chromosomes, not really, because on the you see, this is one chromosome, this is another chromosome, this is another chromosome with different bits, possible solutions, right? So 10, 11, 12, right? These chromosomes. You first generate, right? Then, suppose this is 8-bit. Each chromosome is 8-bit. It has no meaning for you. 8-bit doesn't have any meaning. That 8-bit in binary string can represent any number depending on how you interpret. Say, for example, that 8-bit between 0 to 255, or minus 127 to 128, or minus 20,000 to plus 20,000. It all the scaling factors. What happened? 8-bit, you decide that the range of the number, that you have to decide. While designing the controller, you say, my KP value should be between 0 to, say, 1 to 5, but you are representing that by 8-bit chromosome, so that means, I'm just explaining these things here. If the range of the variable, from, say, between minus 5 to plus 10, right? That means when this is all 0, 0, 0, 0, it is minus 5, and 1, 1, 1, 1, it is plus 10. So that transformation has to be there, the range which you are giving. Otherwise, it has no meaning, right? So this one, you generate a set of chromosomes, possible solutions, and in the back of the mind, you know how to decode the chromosomes depending on the range. You generate 0, 0, 0, 0, what is 0, 0, 0, 0, 0, 0, 0 depends on what the range. You have to give the range. First generation. First you generate a set of chromosomes, then this scaling is there. Then for each chromosome, each possible solution, you find out that the FX value. You find out the FX value, just like I told you. X is equal to 10.1, 10.2 minus something. The first generation, now you find out which chromosomes has got the minimum value. Which chromosomes are minimum value? Say few chromosomes, or suppose you generate 100 chromosomes, 100 solutions, then you found, then you organize them, sort it. Which one has got minimum, next, sort it, right? So now I find out CR1, CR2, up to CR100. So this is the chromosome, which is the minimum, next minimum. So what you do, you go to the next generation. First generation, first you generate and compute it. Then that is meant to be perfect, as I told you, right? Because the solution is minus 400, but you are generating minus 100 to plus 100, clear? Because the initial chromosomes which you have given, the solution may not lie there. Solution may lie in some other places, right? So you first give those chromosomes, first generation, first you compute what is the value. The rest 98 chromosomes, you change it, a new set of solutions. First you get the solutions, which chromosomes gives the minimum value, Keep only 2 or 10, doesn't matter. That's the principle of elitism, right there, but doesn't matter. Next generation, multiple generations, that is they say, multiple iterations, multiple generations. You generate a new set of possible solutions. New set of possible solutions. No. In next generation, you have to generate new. Yeah, otherwise you minus 100 to plus 100, what's the point? Because it will give the same value. You generate a new set of possible generation. How to generate? There is a way to generate it. There is a crossover operation where you generate it. Now see, I'm showing you how to generate. Now see, first one, this point just see here. Suppose I have got a chromosome, one possible solution is first generation, 100111110, one chromosome. The second chromosome is 101 100 10. First generation, these two chromosomes, right? In the next generation, I will generate a new set of population by using crossover operator. What I will do? The first case, I will change this part into here and this part into here. You see here? The second generation is 100 10010. It went to other side and that one came here. Got my point? Did you see the chromosomes difference? A new set of solutions. Or either you can do it that way, single point crossover, or more 2-point crossover. You see, this one. This part is changed. Other things remain same. See here. This part goes here. This part goes here. And this part come here. Other things remain same. So this is how you change the chromosomes. 2-point crossover or 3-point. New set of solutions. Has to generate one set of solutions. Then after a crossover operation, you generate new set of solutions. Did you get it here? This point is important. First chromosome, generation 1, the chromosome was 1001110, right? In the second generation, this chromosome is not there. But there is no point. Already we have known what is its fitness value. So that is 10010, because I changed the patterns. No. See here, I'm doing it in the real domain, you can know it. Suppose the first solution, first set of solutions, possible solutions, let us say, first set of possible solution, X value is 32751 5 192467 235193, this way, first set. So for each value, I computed the value, right? These are the X1, possible solution, X1, X2, X3 in the first generation. In the second generation, what I will do, suppose I do this point, 3 to 7. Suppose I want to do this point crossover, so I will generate 3 to second 5467 and 197515. No, there is no criteria. There is a probability. You just use a high probability, so that with that probability it will change. This is randomly. Just do it randomly, right? So you see the crossover. How do I do it here? You see, these things went here, and these things come here, right? So similarly, I generate a new set of chromosomes, new set of possible solutions, and each solution I have to find out what is the minimum value. Then I will get it, which one is the best. Then I will skip the first few, and the rest of the things, again the same thing. Generate a new set of population, new set of chromosomes. In this way, you continue, and finally you find out a converged solution. Okay? This is a crossover operation. But sometimes what happens, you have to apply a mutation operator. That means here you see, you just arbitrarily flip one particular bit. Say 4, you make it 0. Arbitrarily. Mutation operator with a very low probability. Essentially, you generate a set of chromosomes, that is a population, then try to generate new set of chromosomes using a crossover and mutation operator. Okay? And these are all random chromosomes. And for each chromosome, you find out what is the objective function. And finally, you will find out only those chromosomes which give the minimum value, you will get it. Mutation operation, these things has to be done with some probability, not that you should do, and mutation probability is very less, just little bit, yeah. Crossover explores the current gene potentials. However, if the population does not contain all the encoded information needed to solve particular problem, no amount of gene mixing can produce satisfactory solution. A mutation operator is capable of spontaneously generating new chromosomes. Okay, so the mutation rate should be less. You see, 0.1 probability. Okay. So essentially, randomly generate a possible set of solutions. Each iterations, you generate new set of random solutions. Each iterations, you generate a new set of random chromosomes. And for each case, you compute the fitness value. Right? And while doing it, always keep the best ones to the next iterations. Always keep those things. Okay. Principle of elitism, you see here, these things I keep it. This is first generation, these are the top ones. Then I keep it here. I do not apply the selection crossover operations here. So I put it for the next generation. And in the next generation, new chromosomes will be there. So next generation, these things which are there may not be the best. A new set of things you will get the best. So those things you keep it. You just keep few. Initialize a population with randomly generated individuals. You see, this is the point where the students will get confused. They are coming to solve a control problem, a signal processing problem, or a, so we could say generate a, you see, initialize a population with randomly generated individuals. What you will say? No, that means generate a set of possible solutions. Because we are interested to find out the solutions, right? And those solutions, each solution is an individual. The entire set of pool of solutions is a population. Okay. Select 2 members from the population, 2 solutions with probabilities proportional to their fitness values, apply crossover operation, mutation operation, and do it. Repeat. One minute. One minute. Can you stop these things? Faisal. Hello? Oh, the Faisal Hafiz is coming. Very intelligent student. So I'll do it. What's the time in France now? I don't know. Remember. We are 4 hours back. Okay. So he's early morning. I will tell him that I am teaching this. I've told Faisal to send me a code for PSO. And he sent me the code. Actually, I told Faisal to write a program and send it. I'm going to deliver a lecture. Anyhow. Suppose you want to design a PID controller. Let us see how it will work, which you will do in the assignment. You want to find out P, Kp, Ki, and Kd. So how many variables you have to design? 3 variables. So now you define a chromosome. Suppose each variable, it is a 8-bit. You can decide any bit, 8-bit. So there are 3 variables. So how many variables, what is the chromosome length? 24-bit, clear? So you know that this particular n-bit is Kp, Ki, and this Kd. You know it. That is up to you. Also, you have got a rough idea that what is the range of Kp. Because this, suppose this is a 4-bit, this is 0. Suppose Kp maximum value is 10. So if this 4-bit is 1, 1, 1, 1, that means that is 10. Suppose Ki should be 0.5 maximum. So when these 4 bits are 1, 1, 1, 1, that means 0.5. Because that you decide. You decide that Kp value, maximum value is this much, minimum value is this much. That you have to mention. Because while back decoding, it will decode accordingly. Otherwise, what is the point? So Kp, Ki, Kd, chromosome is equal to controller parameters. Example, PID against Kp, Ki, Kd, represented binary settings, real valued vectors, now more efficient, but now doesn't matter. Even the particles form we do to real valued. Then, how to do it? You see, I will tell you. You generate a chromosome. See here. I'm just giving an example, you will find out. You generate the chromosome, and this is the Kp, Ki, and Kd, right? Now let us assume this one is 1, 1, 1, 1. This is say 0, 0, 0, 0. And let us assume this is also 1, 1, 1, 1. Let us assume. And you have given, that's up to you, that Kp is equal to 15, 25. Ki is equal to 0.1 to 0.9. And Kd is equal to 5 to 7. This is the point you have given, right? Now, first chromosome which is generated is 1, 1, 1, 1. 0, 0, 0, 0, 1, 1, 1, 1. When you decode it, what is the value of Kp? Tell me. Kp is equal to 25. What is Ki? 0.1. What is Kd? 7. Because that is how you have mentioned, right? If you are given different range and this is different, it will decode different value, right? Once you know Kp, Ki, Kd, then you put it in the control algorithm there. You see, UC is equal to this value of Kp into Et plus Ki integration Et plus Kd, these things. You can do the simulation, get the error, then find the function. Which one you want to optimize? You want to optimize this error. Depending on that, which function you are optimizing, right? Now see whether that is a minimum or maximum. This is the function you are, right? See, chromosome PID again, GA for PID, simulate system response for each candidate. Each chromosome will give you Kp, Ki and Kd, right? So for each one, you simulate, you find the output, then compare with the reference, find the error, first chromosome. So there are 40 chromosomes, for each 40, you find out the values. Then decide which one is minimum, and the second minimum. Keep those things for the next generation. Then continue. Got my point? So finally you will find, right? So similarly, for system identification also, so theta 1, theta 2, theta 3, right? You give it. Just theta, you generate chromosomes, okay? Then for each value of theta 1, theta 2, theta 3, you decode it, then multiply it and find out the error, which one is the best. You will do it in the assignment today, you will find out how. This is very simple actually, quite straightforward. First, represent as a chromosome, then decode it back into real time, real number, put that thing in the system and do it. Okay. Similarly, particle sort optimization, we are not talking about those things. And how the PSO work, I think Faisal was talking. This is, Faisal has done it actually. I told Faisal, you do it. See, the program is here, yes. This is the MATLAB program. For a particular function minimization first, you can first check it, then other programs are also given there. So we'll take a break now. Yeah. Yeah. That's fine. No. Yes. Yeah. Yeah. Anything. Yes, you can do it. Any questions you will do in the assignment today? I've got the program I have given you. Did you check it yesterday? Yeah, it's working. Yeah, bit to numerator, how to convert it, chromosome, how to generate chromosomes, these things. Yeah. Which one? No, I won't get it. Just come here. Yeah.
While doing crossover operation, so what is the role of selection like rank with selection and roll it with selection?
That you can do the ruler tool selections. You can do. Usually we do it to ruler tool. So that's up to you. There's so many different type of selection mechanism. Yeah, I understand. Depending on the personal thinking, It doesn't affect much to the system, any sort of selections you do it. There are many types of selection mechanisms there. I use to my students a roulette wheel. We have got a roulette wheel, so we give the selections. But I have never seen in the control applications, it has got much significant effect.
There are various type of crossover like single point, 2 point.
Yes, yeah, similar single point to crossover I have done many times with that.
We are using like a uniform crossover process.
Yeah.
That will provide a better solution, or we can use any type of crossover.
That is a good question, but the question is, the type of applications which I'm doing, I didn't find any significant difference. But if you have got students, you can ask them, you do two-point, multi-point crossover and see what is the performance. If you have got many students, you do it. Otherwise, there is no, but you should understand the concept. Earlier times, whenever the genetic algorithm came fast, people are, we'll start now. So people are doing such type of things which are doing, two-point crossover, relative selections, other type of selections, see what is happening. That was there. But nowadays, you almost established, we use roulette wheel and do it. See what happened? But you have got student, one master students, do these selections and see what is the performance. Then another student, you will see like that. But it is not very significantly changing. Yes. This machine learning, unless you know the history, then you cannot appreciate these things. I will tell you a story behind this. When we were student, in fact, when neural network, you will surprise, the first paper which before PhD I published in neural network in some conference in India and IIT Kharagpur, we are modeling a back propagation MLP of a synchronous generator. I got a student, just sake of fun, I'm doing it. And we wrote the program in Fortran. And implemented it, you will laugh now, PCXT. PCXT means it's a 8080 based processor. Or something 808, something, not a very small computer, okay? During that time I was in Adishi. When I went to England, Steve Billings has got a Sun workstation that is based on the 80486 processor. You may not have heard it. 8080, 8085, 8086, 80186, 286, 386, 486. 1996, when I completed my PhD, I completed my PhD within 2.5 years. But my examination was a bit delayed because of the Christmas time. So nobody is there, it was delayed by 1 month because everybody went on leave. I'm supposed to come by January, but I came end of January. December, there are lots of sale goes on in England. I remember December 23rd, in the afternoon, I went to buy something from the floppy disk. You have not seen those disks, it's not there. 4-inch disk or something I went to, there's a shop called Office, which sells stationaries. When I'm going there, you will surprise. Why I'm telling these things, it is relevant. Those people, in the afternoon I went, it is very gloomy, England is always gloomy. So they were putting something similar to computer and covering it up. Then I told, hey, what is that? Why you are covering it up? They told, no, no, we are not allowed to speak. Today you go and see the British Channel 4 or our television, you will know it. On Boxing Day you come. Boxing Day means 26th. Because 24th, 25th is the Christmas Day, holiday, 26th. They did not tell me. Then I came here to house, to home. Then that's the advertisement in the television. The next generation computer is Pentium 1. Will be available for sale from Boxing Day. 1996, December 26th, in the British soil, in the entire world, those people did not show me. Because they say, no, no, we are not going to, suppose you say. Yeah. So you go and see, you come on Boxing Day, because the shop will be closed. Next day is holiday, next day is holiday. Now from Pentium 1, where are we now, right? 1996. Then what happens in between 1990, 90s, this is 96 was the computers evolution. 1985, people who are working on signal processing must be knowing the person's name is Bernard Woodrow. Woodrow and Stone Adaptive Signal Processing book is very famous. Bernard Woodrow. He is one of the boss in this particular area, and then Rummel had this parallel processing and the computers. There is one guy, I met him in the Rio de Janeiro conference. He is one of the father of this neural network. I think he is Paul Werbs, W-E-R-O-B-S. He is an old fellow. Okay. Going and sitting in the beach in the Atlantic in Rio de Janeiro, I've seen it. Big shots. He's written book and he's the father of the machine learning actually. He has many papers. He is the person who has developed these things. Neural network came up, 1990s. Everybody, entire world, everybody, they will say we are working on neural network, neural network, neural network. And I have seen in Adisi Raulkala, I am not naming the persons, it will be known. Neural network is a, no doubt machine learning people are now talking, they change the name to neural network to machine learning now. Essentially machine learning is neural network when they say, although it is not the case. Linear system identification using a neural network. I asked the guy, why the hell you are identifying a linear system using a neural network with a MLP based network? Is it worth? You tell me, you are all academics. A linear system, a simple discrete parametric model with a least square estimator who can do the job. Why the hell a neural network with the MLP based network, number of layers, there is activation functions, all these nonsense things there. What am I point? So that neural network which was developed during that time, now in recent years, people have given the name machine learning. Actually, machine learning does not only include neural network, but usually they mean the neural network. It is essential neural network based. There is a network, there is activation functions. Okay. The problem with the neural network is, it is very good in the approximation. Although, it can approximate not only the system dynamics, it can approximate the noise. Overfitting, very prone to overfitting. Because there's lots of number of weights are there. You got a point? You give me ample freedom. Suppose to a particular, your child, you give ample freedom. So what he will do? He will do anything, right? He will go to and take drugs also. Okay? He can do anything, right? Neural network is like this. He's a spoiled child. I always say this is a bloody spoiled child. That is we who have done it. Nothing is coming. Okay, increase the number of layers. Increase the number of weights. So why the hell I will increase the number of weights? System is very simple. So neural network, although it has got tremendous capability to approximate a function, it has got a significant drawback. The drawback is the weights of the neural network cannot be interpreted physically. That is the point. So machine learning algorithm that can work fine, but completely useless. Completely useless when I'm saying it. When the question of interpretation comes into picture. Suppose you fit a mass spring damper system model, M, F, K. You have got the model. Now you can say by changing the mass, this thing happen, right? So when you say changing the mass, you have in your mind what you are changing, right? I remember when we are studying applied mechanics, you are all academics, you tell 1 kg per meter square is more or 1 kg per centimeter square is more. Don't think. See, the students should understand that. 1 kg per meter square, that means you take 1 meter by 1 meter and put 1 kg. 1 kg per centimeter square, you take a 1 centimeter by 1 centimeter, then put a 1 kg. Where you will feel more natural, 1 kg per centimeter square. So that way the concept should come, right? Calculation has no meaning. What I point? So similarly, mass spring damper system, there is a model, you change the mass, now you know that the mass is changed, damper is changed, resistance is changed, so damping effect is changed. You change one weight. What is the physical significance you will get? Nothing, right? So machine learning algorithms are completely useless because it cannot be interpreted, right? But it's very good for prediction. Very good for prediction problem, right? Interpretation, zero, right? So if someone is saying that why you are using machine learning for control, working in this particular field for the last 35 years, I will say, I will dump this machine learning in the Pacific Ocean or Arabian Sea. But because students want to graduate and want to publish papers, therefore we are working on neural machine learning. Otherwise there is no point. I'm telling these things, very clear. We have just recently published a paper in deep learning network in computers and electrical engineering. One of my PhD students from Indonesia just published, maybe 10, 15 days before. Okay, and still working on the DQN network. We are doing it. I'm not saying we are not doing it. Otherwise, you cannot survive, right? The students want. So, machine learning has its own problem, but it's a good predictor, no doubt about that. It's a good predictor. It has its own applications. But in control applications, ML can model system dynamics, detect faults, or learn optimal control policies. It can learn it, no doubt that. But it can model system dynamics without giving any interpretable capability. It can learn. Neural network can learn it, right? It can fit it. They adjust internal parameters, weights in a neural network to reduce error, right? Training and learning from data. Nowadays you will find Google, Facebook, all these things. They have got a huge machine. I'll tell you, this is the exact thing I'll tell. We have got a professor back in REC Raulkela, amateur astrologer. In India, he is amateur, not a professional. He is a professor, he is a very good person. And I asked one day, sir, how do you learn this astrology? He told, I did not learn anything, you see. In our house, my father was a priest in Puri. So, he is a good astrologer. So, we have got many charts, you see, training data. We have got many charts, many people's astrology charts. And the results are written there. So, I learned it, just mug it up. I know if at this point Brihaspati will be there, this will happen. if this point Sony will be there, this will happen. So I just mug it. There is no formula. So now I found somebody gives me, then I see it. Okay, Jupiter is in this place, Rahu is in this place, so this will happen. You got a point? He is not learning anything, just mugging it up, overfitting. You see, core fitting. Okay, so he has told me. So they learn from the data. There's some training data. If someone's chart will come, whose chart is not there, he cannot say anything. The similar type of things should be there because he has learned from that, right? So, the Google engines, they will fail to do prediction because their training data may not have these type of things, okay? Machine learning algorithms requires a lot of data for training, and that is the one of the disadvantage of the machine learning techniques, right? Given many input-output pairs, a neural network can map a system into this. But I will tell you, with 700 data points, we can map in most of the practical nonlinear systems into a simple parametric models. 700 data points is enough. Neural network will not do it. Neural network requires more number of data points. Okay. Machine learning has got one category supervised learning, another is unsupervised learning, reinforcement learning. Supervised learning, you know it because you give the same input to the model, same input to the system, mimic it, right? Supervised. Unsupervised learning is very simple. You are doing every day. You will find in this particular place, there are people from Maharashtra, people from Andhra, people from Tamil Nadu, right? So whenever you are sitting here, nobody is telling you, but you cluster. Okay, you learn from this. Okay, where are you from? Oh, I am from Chennai. Where are you from? I am from Madurai. Then we are together. Nobody is going to tell anything. You see, you learn by yourself. Unsupervised learning, you cluster together and you make it, right? Unsupervised, there is nothing to tell. Children are playing, they will get connected accordingly. Reinforcement learning is a very fashionable catchword now. Reinforcement learning, right? This is neither supervised nor unsupervised, right? Neither supervised learning or unsupervised. So reinforcement learning is like this. You do a job. You do your job, right? Now once you do your job, you will get a reward. You will get a reward. Say for example, I am teaching here. Professor Rahulkar told me that if you teach well, you will get a T. If you don't teach well, you will get a chocolate. Got my point? So I don't know anything. So I am teaching. By the time I go out, he gave me a chocolate. That means I talked nonsense in my last lecture. You got my point? Because the reward is less, only small chocolate, not tea. Okay. Then he will say, you will teach excellent. I will give you a treat in Taj Hotel. Okay. So what suppose he is giving me a treat in a local hotel, then I say that my performance is bad, I have to still improve. Exactly the same principle, the things happen. Reinforcement learning, okay, you take action. You generate a control signal and see the performance, right? Then the learning policy will say, if it is good, then they will give you a reward. You will get a reward. That reward, that will decide that what action you have taken, you will continue with a similar type of action or you will revert to other type of action. Right? Second point is, Because it depends on the reward, right? Which type of reward? That depends on the performance. Now suppose somebody say, if you will do these things, you will get 2 lakhs rupees. And somebody says, if you will do these things, you will get 1,000 rupees. So naturally you tell me where you will work better. 2 lakhs, you will. So your performance is depending on the reward function, what you are getting the reward, right? Got a point? So, reinforcement learning like this, okay? Nobody is telling anything. It is unsupervised. Nobody is telling anything. You work. Why it is also not unsupervised and supervised? You are also getting a feedback. There is little bit of supervision is there. You are getting a feedback. Okay? So, here you see, reinforcement learning is not supervised because it does not learn from the input or pairs. It just takes action. It is not unsupervised also because you are getting a reward. Okay, so from the reward you can know whether you are doing good or you are doing bad. Got the concept here? And which is critical in reinforcement learning? Critical is the reward function. Depending on the reward function design, if you change it, the performance of the reinforcement algorithm will change. Very fashionable catchword now. Reinforcement learning, everybody is using reinforcement learning now. You can read all these things. See, all these things I wrote it here. This is just for sake of delivering lecture. I don't have that slides. I think I kept somewhere. Fuzzy controller. Fuzzy controller. Many people, anybody working on fuzzy controller, students? Fuzzy controllers. Lopte-Jade developed the fuzzy controller and fuzzy principles, all these things. There is a guy in the MIT lab who works in the optimal control. So in a keynote speech, I have not gone to that conference, but I have got the slides. Somewhere I lost it. I will find out somewhere. You will be surprised. The way he blasted Lopte-Jade in that keynote speech, he says that your fuzzy controller can do everything, but I can show you that the optimal control can straightway do the same thing what your fuzzy control is doing. Fuzzy control is not superior. I can show it clearly. So similarly, people say machine learning can do many great things, but then many other controllers can also do the same job, right? There is no need of machine learning. Why are very complex things? It requires a lots of data sets, right? Reinforcement learning is becoming popular because it does not require lots of data. You change and also you don't need anything. You just get an action, you perform one control action, get a reward. Depending on the reward, you change your action, right? But see, these things, machine learning can generalize well. People are writing it. I just copied from somewhere, but I don't agree. Generalization capability of the machine learning is a very difficult problem because it unnecessarily overfit. The bias variance dilemma is a serious problem. Okay. So what we are writing here, it has, you must, because you are academics, therefore I am telling you. You must be very careful, right? I will give an example. 2006, I was in a conference in Singapore. In the Singapore conference, the keynote speech is being given by the person Leonard Leung from Sweden. He is the #1 person in system identification. Around 500 people are sitting in the Hyatt. I remember he is delivering, Leonard Leung is talking. Leonard Leung is a big boss, #1. There is a person on the backside, myself and Edward were sitting there. He asked questions. He told Professor Leung, the results which you are showing is wrong. I looked at who is telling Leonard Leung is talking. Who is shouting in the conference, keynote speech that is wrong. Leonard Leung is a very gentleman. He told, no, how can you say it is wrong? No, I have got 11 PhD students. I have taken this example, it did not work. Why you are showing this result here? People are there like this. You got a point? This type of generalization is the standard thing. Generalization how can you generalize? There are many number data is corrupted by noise. There are so many words. It will overfit. It will overfit. Generalization capability is an extremely difficult thing. Okay. Now see here. Classical controllers PID, MPC rely on accurate system models, struggle with nonlinearities, uncertainty and dynamic environments, which is not true actually because MPC is there for nonlinear systems as well, but doesn't matter. This is model-free learning from interaction. That is the one thing. It does not require any model. That's the advantage. Capable of discovering optimal policies based on the reward. It can automatically learn. Because I am not getting any reward, that means I have to change my action. Bridges control theory with machine learning. I will tell you from my experience, machine learning can be used as a supplement to the classical control. Machine learning can be used as a, just like a dessert. A dessert cannot be your full meal. Full meal will be rice, chapati, curry, right? That is the full meal. Dessert is the machine learning. It is just complemented. You cannot use machine learning as the major thing. You got my point? So that point keep in mind as in academics. You should be very careful. Bridges control theory and machine learning. I think I mentioned somewhere. Reinforcement learning is a branch of machine learning where an agent, just like in genetic algorithms, we have chromosomes. So here you have the agent. Agent is the controller. The agent is taking an action means the controller is generating an output. Agent is the controller. The name agent in reinforcement learning terminology is the controller. You see, reinforcement learning is a branch of machine learning where an agent, I have mentioned controller, learns to make a decision by interacting with the environment. Environment is the system. Environment is the system. So agent is the controller, environment is the system, and that is the state. Statement is the same thing. System states. Maximize the cumulative reward over time. How much? So it will go on changing its action until it gets more reward. Unlike supervised learning, which relies on labeled data, reinforcement learning is based on the idea from learning from trial and error. It will learn it, you see, learning from trial and error. It generates an action, do not get any reward, it will change the action. Get the reward, good reward, modify it. I mean, reinforce the same action. The agent takes action, that is, agent generates some control actions, controller, in an environment, in a system, observes the outcome of, in terms of rewards or penalties, and adjusts its strategy to maximize the long-term cumulative reward. Okay. See here, standard control theory reference, controller, manipulated variable, plant, right? Now here you see the same thing, you see, environment is the system, right? The system is giving you states, okay, the output or anything. Agent is the controller. The controller will take the reward from the system will give the reward, and it will observe the state, and depending on the policy, it will take action. Policy means, suppose, say, for example, agent is the controller. So it has got a policy that if I get this reward, these things, I will do it. Now suppose he does it, and he is not getting any reward. So you change the policy. Change the policy means change the control algorithm, little bit. Okay, so that's the policy. And you change the policy update. Policy update means how you, just like we do it. We don't get any reward. Suppose you are working in the power system, and you are not getting any reward from the department. So you change the policy that is from power system, you change to signal processing. Okay, and they get the reward. Yeah. This agent is essentially a controller. Yes, the policy change it, depending on the reward. See here, I have mentioned the relationship. Now this is a DC motor. The program is there. I don't know the program code I have given you somewhere. This reinforcement learning controller, you see here. Set point is 300 radian per second. Sorry. Then it changed to 275 radian. Now see here. And then it changed to here. The reward function is here. The reinforcement learning controller, right? It is working. MATLAB code is there. These things I cannot tell more about that because by the time I was too busy, I told my one-man PhD student, Gunman, he's an Indonesian chap. So he did it, he sent it. If you need anything, if it doesn't work, then you just send me an email or to Professor Rahulkar and I can pass it to him. So he will give you the code. Similarly, another example here also, automatic voltage regulator. Again, you see the reward function changed here. The reward function, we change it. Now, this is the response here. Voltage output. The code is here. The code is there. You see, commonly used design terms and the reward is here. Different types of rewards. It all depends. You change the reward function, things will change. That you have to do the research on that. There are many people are working on the reinforcement learning controller, changing the reward. Okay. Yeah, same thing. These handouts are given to you. Yeah. Only the Lyapunov stability handout, I'll change it and now value means the reward based function. Policy, they are almost the same, you see. What is that? I don't have an answer to that actually. I don't remember, it's not in my mind. Yeah? No, cost function is different. There is no relationship. You decide what reward you will give. No question of cost function. You see, given an analogy, things will happen. Suppose the cost function is, suppose you have, your child is there, you decide your cost function, that how much mark you secure and what is the error between the 100 and the mark. That is the cost function. Now, based on the cost function, this is the cost function for all of us, you. For you, and the same cost function I am also using. The difference between the mark you secure in the exam and the 100 mark. That square is the cost function for all of us. But you have told to your child that you will get 95, okay? I will take to Taj Hotel for dinner, and I will tell my child that if you get 95%, I will take you to the beach. And other person will tell his child, if you get 95%, I will give you a bicycle. So that reward, the same cost function is same, but the reward is different. That depends on you. You got my point? So cost function is same, but reward is different. That you decide. Deep learning, again this deep learning. Deep learning means multi-layer perceptron. I'm telling when at the beginning it came, the people started developing theory, how many number of neurons, what is the type of the activation function, okay? That will impact the performance. That is the usual research, 1990s, people do it. Number of layers also was there. Then suddenly a theory came, radial basis function network came, and it proved that any nonlinear system can be mapped by a single layer. So that thing went away. No question of number of layers. Earlier MLP-based network. This convolution neural network, CNN, or that is called the deep neural network, it came with the application in mind, the image processing applications, deep network. There are multiple layers, all these things, okay? People are using in control. People are using in control, I am telling you, not that people are intelligent. I ask my students, they are all saying we are using deep network. I told them, how come these students are there using deep neural network? They say, sir, we have got a toolbox available. Reinforcement learning toolbox is available. Deep neural network toolbox is available. The neural network toolbox is available. Okay? What do you learn from that? Nothing learning. The machine is learning. You are not learning anything. You just key in. I always tell to my students, I can pick up someone from the Queen Street and they can do the job. What the hell you are doing? So deep neural network, so there is no need of understanding anything, why it is happening, right? There is one group who was working on the power quality, they are doing the final year projects. They are using a deep neural network. Deep neural network will generate features. They will generate features and classify it. Which features they are generating, you don't know. Automatically, you see, there are so many layers. Which feature, there will automatic feature generation. Which features, you don't know. Whereas you generate features using overlays, using S transform or anything, you know it. Here you don't know it. Everything is black box. But people are doing it, you do it. No one knows. See, when you are sitting, understand the point, when you are sitting in the computer, you are not writing the program. What is the point in putting 5 layers or 6 layers? You just put it and you see some results, you get it. It is completely bogus. You got to, now you don't have any clue. Even reinforcement learning controller, I remember when Joey was doing my PhD in 2018, she was writing program, reinforcement learning controller. Gunman is doing, I told Gunman, what is that? No, Dr. Swami, RL toolbox is there. Surprised. As an academic, should I encourage? I will not encourage. But this is a part of the game. We have our own career and all these things. The boss is sitting there. Okay, this is recorded, I don't care. Okay. You got a point? Is it necessary to use it? Why I am telling these things to? I can tell with full confidence that I am able to tell it because I have worked in neural network, I have worked in the classical control, I have worked in the LQR, I have worked in fuzzy logic, I have done all these things myself. I have worked in mathematical control theory, proving lemma theorem, all these things. I have also worked in power system. I have worked in system identification. If you see my publication profile, I am not telling as a proud thing. Because I have done in many cases, I can tell. Steve Billings could tell because he has gotten 800, 900 papers. He has published around 50 to 100 papers in neural network. He can tell neural network is useless. He has himself has published 100 papers. You got my point? We know what is that. Okay. So, I think we will close the lecture today from here. And thank you very much because on the background lots of things